Okay, when you get down to it, Chapter 11 really is all about the mole ratio. Now back in Chapter 10, we used molar mass to go back and forth between grams of something and moles of something. So that was our molar mass. In Chapter 11, what we're using is this new mole ratio, and the mole ratio is given to you using a balanced chemical equation. And what it does is it allows you to go from moles of one substance to moles of another. So what we've discovered is that there's no direct way to go from grams of one substance to grams of another, but using this mole ratio, we can go from moles of one thing to moles of another. So the first several problems in Chapter 11 are all about just using this mole ratio. Number 44 asks you to interpret a balanced chemical equation in terms of particles, moles, and mass. Okay, in particles we can think of it if we zoom down to the molecular level and we're proceeding sort of as it happens. So what our coefficients tell us is that there are 4 aluminum atoms that will react with 3 O2 molecules to produce 2 formula units of aluminum oxide. We can scale that up using moles. Okay, if we go from particles to moles, we multiply everything by the same number, so we actually have the same number of moles interacting. So moles allow us to see things on a much larger level. And again, we have 4 moles of aluminum reacting with 3 moles of oxygen to give us 2 moles of aluminum oxide. In order to interpret it in terms of mass, what you need to do is you need to use this molar mass that we went over earlier. Okay, so you use the molar mass and you convert your 4 moles of aluminum to 107.92 grams of aluminum. You convert your 3 moles of oxygen to 95.99 grams of O2, and your 2 moles of aluminum oxide to 203.91 grams of aluminum oxide. And you do that by just multiplying the number of moles by the molar mass. In number 53, we're asked to come up with a balanced chemical equation based on one that's described in the book, and then figure out what the mole ratios we would use to convert between one of the reactants and one of the products. Okay, so the first part we just balance the equation, and that's something we've done in the past way back in Chapter 9. Once we have our balanced equation, we can use the coefficients in the equation to get the mole ratios we would need to convert between moles of one substance and moles of another. So if we want to go from magnesium oxide to magnesium chloride, we look at the coefficients of those 2 substances. So here, magnesium oxide doesn't have a coefficient in front of it. Basically what that means is the coefficient is 1. It's the same case for magnesium chloride. That being said, the mole ratio then is 1 mole of MgCl2 per 1 mole of magnesium hydroxide. Okay, what that tells us is that each mole of magnesium hydroxide that gets consumed will produce 1 mole of magnesium chloride. In order to go from our hydrochloric acid to magnesium chloride, again we look at the coefficients for these 2 substances. Coefficient for HCl is 2, coefficient for magnesium chloride is 1. So if we want to go from HCl to MgCl2, we use 1 mole of MgCl2 per 2 moles of hydrochloric acid. And again, what this tells us is that each 2 moles of hydrochloric acid that are consumed will produce 1 mole of magnesium chloride. Okay, in number 61, what we're doing is we're applying a mole ratio from a balanced chemical equation. So you're given the equation CaC2 plus 2H2O goes to CaOH2 plus C2H2. And you're starting with 5.5 moles of this calcium carbide, the CaC2, and you're asked how many moles of acetylene, C2H2, you can come up with. Okay, we're converting between moles of one substance and moles of another substance, so the mole ratio is what we're going to use to get back and forth between those 2 things. In this case, the coefficients for both C2H2 and CaC2 are 1. So the mole ratio we use here, we want to cancel out our moles of calcium carbide, is 1 mole of acetylene gas per 1 mole of calcium carbide. If we set it up right, our moles of CaC2 will cancel out, and you'll actually end up producing the same number of moles of acetylene gas as you started out with in terms of calcium carbide. So that's number 61.